Hello everyone. So let us start today's talk on the introduction to an application of synchronization theory. I think it will be a very interesting talk, and before going to the talk, let me introduce Dr. Sirshendu Mondal. He's an assistant professor in the Department of Mechanical Engineering, NIT Durgapur. He has done his PhD from Jadavpur University and with the DAD fellowship and partly in Germany. And then he did his postdoctoral work from IIT Madras, and he has very good publications in classic journals like Journal of Fluid Mechanics and Chaos. And he's very much well known for his work in the experimental thermoacoustics and synchronization theory. So we think we'll have a very interesting talk today. And without further delay, I'll just hand over this session to Dr. Sirshendu Mondal, and let us start the talk. Yes, please continue.
Good morning to all of you. Thank you, Chandran. Thank you for the kind introduction. And I'm also thankful to the organizer of this lecture series of the mechanics discussion. And again, thank you all for joining here. So my topic is Introduction to and Applications of Synchronization Theory. So in this talk, essentially I will cover, in the first part of my talk, I will cover the basics of synchronization theory. And in the second part, I am going to give you several examples or applications of synchronization theory. So, so the basics of synchronization theory will be needed so that the results applying this theory can be understood and appreciated. So let us start with the quote by René Descartes. He said, "Give me the matter and motion, and I will construct the universe." So if motion is so fundamental, a popular possibility of motion is something which exhibit or which shows some degrees of repetition. That is what we call oscillation, right? And for example, our heart. So our heart is an oscillator. Now, if we can think of a situation when any natural oscillating process or oscillator, when you have more than one oscillator and they are basically feeling each other's motion, then what will happen? Then if we can consider a system, again from biology, that is a cardiorespiratory system, and we can see that the motion of lungs and heart, and they actually feel each other's motion. So we can say that when we inhale or exhale repetitively, essentially that influence the way our heart beats. So what we are calling that the oscillators feeling each other's motion, in scientific term we also call it the oscillators are coupled. Then the question comes, what role does the coupling play? Now, when there is a coupling, when two oscillators are actually coupled, the system's property or system's behavior, that means the properties of those oscillators will generally change, sometimes most drastically. Now, if we want to couple two oscillators, it's always better to know the possible consequences beforehand. For example, I can say that sometimes it may so happen, then if we couple two oscillators, the oscillation will completely die down. I mean, that complete stopping of oscillation may be good for some systems, may be disastrous for others. For example, as you all know about the aeroelastic flutter, that is a dynamic instability, which is very unexpected for the system. And then the stopping of oscillation for aeroelastic flutter will be good for the system, but if you consider the heart's oscillation, and that can be dangerous. So beforehand, we need to know what will be the consequence if we couple two oscillators. So essentially what will happen, the time scale of those oscillator or of the oscillating processes will change, and then they will adjust. So the interesting part is, if you couple the oscillators cleverly, they can oscillate synchronously. That means the time scale will adjust such a way that the time scale of two oscillators will be I mean the two oscillators will have the same time scale, or they can have a linear correlation, right? For example, it can show like this, the synchronous motion, and for that we can conclude that this synchronization is the most fundamental phenomena that occurs in oscillating processes. Now let us, so this phenomena is, I mean, defined as an adjustment of the time scales of oscillation due to the interaction between the oscillating process, right? So this phenomena, which is known as synchronization today, was first observed and described by a Dutch scientist, Christian Huygens, who saw that when two pendulum clocks which were hanging from a common support or common beam, and they were actually oscillating synchronously. They were actually their oscillations were completely synchronized, and so this is the hand-drawn picture by Christian Huygens. So what he observed actually like this. So he saw that the oscillation moved always away from each other, right? And interestingly, he described this phenomena as sympathy of two clocks, right? So this is in 17th century. Later on, in the middle of 19th century, the Lord Rayleigh also observed this kind of phenomena in different system, in acoustical system, and he observed that two organ pipes, which sounds, I mean, which are distinct but similar kind of pipe, which were kept side by side, and he observed that they actually sound in unison. So that was again an example of synchronization. And more interestingly, he observed when this influence between these two organ pipes are maximum, they actually stop sounding. I mean, there is no sound in the oscillation pipe. That means whatever the pressure oscillation inside the organ pipes were completely suppressed. Right? Now, let us look at what are the systems from which we can expect such kind of phenomena or synchronization. Now, anything that is oscillating in principle can be called as oscillator, but we are interested in those systems which are capable of demonstrating the self oscillation or self-sustained oscillation. Now, this is again a broad class of oscillation or oscillators which are characterized by the following features. That is, they do not damp. So am I talking about any conservative systems? No. Even in dissipative system, there can be self-sustained oscillations if we have a continuous supply of energy or internal source of energy. So if we have that, we can have a self-sustained oscillation even in dissipative system. And the second feature is they oscillate by themselves. So it essentially indicates that the oscillation in the oscillator should not be maintained by any external kicking or from the kicking from the outside. And the third and most intriguing feature, that is the shape, amplitude, and the time scale. That means whatever the waveform or amplitude and frequency of these oscillations are chosen by the oscillating systems alone. So that means it should not be influenced by the initial condition. So it should be influenced only by the internal parameters of the oscillators, right? So there are several examples of self-sustained oscillation. For example, the grandfather's pendulum clock is a self-sustained oscillation. Here the source of energy is, I mean, maybe in form of a coiled the spring, or nowadays it's battery, it's a electrical energy. Now, as I said already, the heart is also a self-sustained oscillator, and there can be a chemical oscillator, which is a popular kind of chemical oscillator. There are many more, which is known as BZ reaction or Belozov-Zhabotinsky reaction, which actually in the medium they keep exhibiting a self-sustained oscillation. Right? Now, having described the self-sustained oscillation, let us couple them. So once we have coupled the self-sustained oscillation, so there can be different kinds of situation. Now, just consider that we have two pendulum clocks, and I mean, they are fabricated by the same brand, and even if they are similar and same brand, there can be a slight difference in mechanical properties or mechanical parameter, and because of that they can show a different time, right? Or you can say that at different point of time the blobs of the pendulum or the pendulum blobs will be found at different location, right? So basically they are, I mean, they are having a slightly different time period or frequency. Now let us couple them again, as the Christian Huygens did. Let us couple them through a common support, and this common support should not be extremely rigid. And why so, we'll see in a while. So let them hang from a common support or common beam, and then their period basically will adjust, and their time period will be adjusted, and they will start oscillating in a common frequency or common period, which is known as frequency entrainment or frequency locking. So even though initially the time period or frequency were slightly different, with coupling, when the information from one pendulum clock is transmitting through the beam or common support and reaching to the another pendulum clock, they are actually adjusting their time period, and they start oscillating with a common period or common frequency, which is known as frequency entrainment and frequency or frequency locking. Now, what are the factors that will actually determine whether two oscillators, when they are coupled, will synchronize or not? So there are essentially two factors. One is called coupling strength, that is how weak or strong the interaction is. So we have talked about this coupling through the beam for the example of pendulum clocks. Now, how strong or how weak this interaction or coupling, that is one factor. Now, as I said in the previous example, the beam should not be absolutely rigid. That essentially means that if you are considering a absolutely rigid beams, then your coupling strength will be zero. So there will be no information transmission between these pendulum clocks. So so one thing here I need to mention that, I mean, many times when you are dealing with experimental systems and you have two oscillator, whatever oscillating process you are dealing with, and you couple them, many times it's very difficult to quantify this coupling. So but in mathematical terms, it is clearly understood that there will be some kind of interaction which you can vary how strong and how weak it will be. And the second factor is the frequency detuning or frequency mismatch. So I mean, when they are coupled essentially, so when two oscillators are when they are decoupled, so when two oscillators are decoupled, there is no coupling between them. What is the frequency mismatch or frequency difference between them? That is also a deciding factor whether it will synchronize or not. So it is say delta f. So let small f1 and small f2 is the frequency or their natural frequencies when they are actually decoupled. Now let us consider that capital F1 and F2 are the frequencies when they are actually coupled. So the frequency difference delta capital F is the frequency difference when they are coupled. Now what will be the effect of this frequency detuning on the coupled dynamics? So let us look at a very simple plot. So here basically we are looking at the frequency after coupling or dependence of frequency after coupling on the frequencies before coupling, or the difference of frequencies before coupling. Now as you can see, this is the line which is in the x-axis. That means the frequency after coupling becomes exactly zero. That means the frequency has entrained. So we can say for a for the frequency detuning, which is not very large, so in this region basically, when you couple those oscillators, your final frequency or the coupled frequency will be entrained, and the sequence and the synchronization will occur. And we can also conclude from this fact, I mean, that this region, that is the synchronization region, will vary with the coupling strength. So as you increase the coupling strength, the region of synchronization or the zone of frequency detuning will also increase, right? Now the concept of frequency entrainment or frequency locking says that there will be the matching of frequencies. That means the frequency of both oscillators will be exactly same, and the manifestation will be like this, or I mean maybe like this. So your two oscillators will be oscillating in exact same frequency, so the manifestation can be like this. The manifestation can be also like this. Now these two situation cannot be differentiated by the concept of frequency entrainment or frequency locking. So here we are going to introduce a key notion of synchronization theory, that is phase of an oscillator. So we will all know that what is the definition of phase. So phase essentially indicate the state of an oscillation. So in I mean, instead of describing in terms of time, we are describing in terms of degree or radian. So it's essentially the state of an oscillator. So it seems that it does not provide any more information when we talk about phase, but actually the phase difference does. So this is how we define phase. And now if we look at the phase difference between two oscillators, we can see that for the first case, when these two oscillators are manifestation of two oscillators are like this, the phase difference is close to zero, right? I mean, there are two waveforms of two oscillators, and you can understand the phase difference between these two oscillations are either exactly zero or close to zero. And in this situation, we call it in-phase synchronization. And the second situation, where these waveforms are 180 degrees apart, or their phase difference is close to pi or 180 degree, we can call it antiphase synchronization. So in general, we say that the on between the phases of your oscillators is termed as phase locking. So we have defined frequency locking, that is the matching of oscillation, and then we are also defined phase locking, which is essentially development of certain relationship between the phases of the oscillators, right? So we are going to keep those notion in mind, phase locking and frequency locking. Now let us also look at some counter example of synchronization to reinforce our understanding of synchronization. So the first one is let us look at the synchronization versus resonance. So resonance is again a well-known phenomena for an oscillator. So if we take an example of magnetic pendulum, so this is a pendulum, and the natural frequency or the frequency of its free oscillation, let's say it is f0, and this pendulum is this periodically kicked by a magnetic field, and the frequency of that magnetic field is f, let's say. Now the oscillation of this pendulum will be visible only when this frequency of magnetic field will be close to the natural frequency of the magnetic field. So this is a popular resonance phenomena, and this cannot be called as synchronization, because the pendulum does not show the self-sustained oscillation, or it has not it is rhythm of its own. So because of that, we cannot call it synchronization phenomena. The other example is the synchronous variation of two variables of a single system. Let's say again, if we think about a simple harmonic motion or a pendulum motion, then if we think about two different variable of position and velocity of that blob, then both will be oscillating in a same frequency. I mean, that is pretty obvious. Now if you think about these two variables of velocity and the position of the blobs, I mean they will be definitely showing the synchronous variation. So we are going to use this term synchronous variation, but we cannot call it a synchronization. The reason is you cannot separate them. So in a pendulum or any simple harmonic motion, if you want to separate this position and velocity, I mean there will not be any oscillation. So we cannot call it synchronization. Right. Now there are different ways of classifying synchronization. So for basic understanding, let us have this classification. So it depends upon the dynamics of your oscillator. So whatever oscillating processes you are dealing with, it can be periodic, it can be aperiodic, or any irregular dynamical state, and depending upon that, depending upon that, your coupled dynamics or the dynamics upon coupling will vary. So synchronization situation or synchronization phenomena can be classified as the dynamics of your uncoupled state or uncoupled dynamical state, that is periodic or aperiodic. It can also be classified depending upon the nature of coupling. So here we are going to see two different types. That is, one is called bidirectional coupling. So from schematic you can understand that there are two oscillators essentially, and both are affecting each other. That means so both are affecting each other. So essentially the coupling is bidirectional. Whereas in unidirectional coupling, you have coupled two oscillators such a way that system 1 is affecting system 2, but the system 2 is system 2 cannot affect system 1. So this is also called forcing. So basically when we force a system, force a oscillatory system, it can be, it is considered at unidirectional coupling. And the eventual synchronization phenomena is termed as mutual synchronization and force synchronization. So bidirectional coupling is also known as mutual coupling. So the phenomena is known as mutual synchronization, and the unidirectional coupling or forcing, which leads to forced synchronization. So with this, so far we have basically dealt with two oscillators. So if two oscillators can synchronize, more than two, or ensemble of oscillators can also synchronize, right? So let us just look at the example of ensemble of oscillators and oscillatory medium. So there is a very natural example of synchronization of fireflies. So that essentially start flashing in unison. So when they have
Sorry.
so what we call them, basically an ensemble of globally coupled oscillators of fireflies, and they are found to flash in unison, right? The another interesting example is a large applauding audience. So you might have experienced in a big hall or with a big audience. So after a let's say a orchestra, so when they start clapping, so after some initial transitions, a large body of the audience start clapping in unison. So that is also an example of synchronization for a ensemble of oscillators, right? And this is an example of, again, this chemical oscillator, which is known as Belousov-Zhabotinsky reaction. So sometimes we cannot differentiate the oscillatory element or the oscillating process. So it behaves like a continuous media which is oscillating, and we call them oscillatory media. So this is one of the example of oscillatory media, a chemical reaction. So with this, let us move on to with this basics of synchronization theory. Let us move on to the applications of this theory into mainly in engineering systems, and I will also talk about some other systems. So I'll basically divide it in two parts. So one is, few studies which have accomplished, and that there is a published work, and also some ongoing research work. So I will talk about them one by one. So for every system, I'll just describe the system, and then how synchronization theory is applied, and what is the outcome of this theory, etc. But I'm not going to go into detail of the results and discussion or many more results. So mainly I will be highlighting what is the application of what extra we can extract from the system if we apply synchronization theory. So
Okay,
these
can
are
I
the
interrupt
very
you a bit?
good books. Yeah, sure.
Yeah, so can you go back to the examples that you gave? So you gave an example of the clapping in a large audience, right?
Yeah, yeah,
So,
yeah, right.
can we call it a forced synchronization or mutual synchronization? Because we are
No,
giving a
it's mutual
trigger.
synchronization. Trigger, we are not actually, no, the starting point is maybe triggered because something is being ended, some program, some performance is being ended. Now once people have started clapping, they have, initially they have no communication. Now when you are clapping as an individual, when when you are clapping, actually you are also hearing the clapping sounds of others. So your brain basically trying to couple with other sound. So
Okay.
I mean, same thing is happening to all other audiences. Now when you have a different kind, so let's say 5 people have started clapping synchronously. So you are hearing a little bit louder sound and you are perceiving that particular frequency. So your brain unknowingly will follow that frequency and start uploading or following that particular frequency, and that way a lot of people will join in that frequency, and then there will be eventual synchronization in the audience.
Okay, fine. And can you give some physical or engineering applications of the force synchronization, like where we can observe them?
Yes, I will. I mean, the second part is, I mean, full
Okay.
of application. I mean, I will one by one, I will describe mutual and forced. Both of them are there.
Okay. Thank you. Yeah. Please continue.
Okay. So, yeah. So here I am going to take up one, a few application area of synchronization theory. The first example that I am going to take up, that is thermoacoustic instability, that is the thermoacoustic systems essentially. So in thermoacoustic system, so let us consider, we know, I mean, there are several example of, the practical combustors essentially. So in combustors, the combustion process are unsteady processes. So due to turbulent environment, etc. So combustion process itself is a unsteady process. Now sometimes inside combustion chamber, the unsteady combustion process gets coupled with the acoustics of the combustion chamber, right? And when this happens, there is a positive feedback loop that is set off between this acoustic field of the combustion chamber and the unsteady combustion process, right? And this leads to a very large amplitude pressure oscillation inside the combustion chamber, which is known as thermoacoustic instability. Now essentially what happens, some amount of energy from the combustion that gets added to the acoustic field of the combustion chamber, and because of that there is the amplitude of oscillation or pressure oscillation grows, and then finally because of some non-linearity it saturates with a constant amplitude, and that what is known as thermoacoustic instability. Right now, this thermoacoustic instability essentially leads to a high level of vibration in the system, and it can lot of damaging consequences for the practical combustor. So for a long time, people are trying to identify, describe, and also control this thermoacoustic instability, or to suppress this high amplitude of oscillation or vibration in the system, right? Now these are the basically flame image, or more precisely chemiluminescence image, when your combustor is a stable operation. So you can just see the turbulence environment here, but the oscillation is not clearly visible. But as you go towards, whatever the control parameter, for our case it was the equivalence ratio, and reach to an unstable operation. Now you can clearly see the periodic oscillation in the flow field, right? So from a stable operation to unstable operation, there is a development of high amplitude pressure oscillation. Here it is shown in terms of flow field oscillation. Now people have described this transition. They have proposed different routes for this kind of transition. So one of the route is intermittency route to thermoacoustic instability. Right. So let us briefly look at this. So the stable operation is also known as combustion noise, which is characterized by a small amplitude aperiodic pressure oscillation, whereas the thermoacoustic instability, which is characterized by the very high amplitude pressure oscillation. And prior to thermoacoustic instability, it goes through a intermediate state where this aperiodic, small amplitude aperiodic and large amplitude periodic oscillation appear alternatively in a random fashion, which is known as intermittency. So this is a well-known route for the intermittency route for the transition to thermoacoustic instability. Now this characterization is done completely looking at a single variable, that is the pressure oscillation, right? If you look at the other variable, that is the flame oscillation, still you can end up with the similar kind of transition roots. So as I said, that this oscillation is essentially a coupling or feedback between the combustion process, that is, let's say, heat release rate oscillation, and the acoustic process, that is pressure oscillation. So looking at a single variable will may not describe the describe the situation or the system properly. So what we did, for bringing the synchronization theory, we are going to cast the system as two mutually coupled oscillator. That is, one is turbulent reactive flow, that is essentially the combustion process, combustion reactive flow, basically flame oscillation or heat release rate oscillation, and the other one is acoustic oscillator, that is the pressure oscillation. It may be acoustic pressure, acoustic velocity. So these two oscillators are, so we are casting a thermoacoustic system as a mutual coupling between these two oscillating processes. Now, what will happen in this dynamical state? So let's look at the what they behave during combustion noise or stable operation. So here basically red curve indicating heat release rate, that is the turbulent reactive flow oscillator, and the black curve is acoustic oscillator. Now, as you can see that during combustion noise, their evolution is not in sync. I mean, they are basically evolving asynchronously. Now, if you look at during thermoacoustic instability, and their evolution is very much in unison, and they are evolving synchronously, right? So there are intermediate states. So as we have already mentioned, that is intermittency. So during intermittency, you can see that there is a portion that is showing synchrony here, and there is portion where is basically showing asynchronous oscillation. So again, synchrony and asynchrony basically appearing alternatively in random fashion, right? So from this phenomena, we can conclude that the onset of thermoacoustic instability as a synchronization of two mutually coupled non-identical oscillators, right? So the crux of the matter is, when we apply synchronization theory, the route to thermoacoustic instability is redefined. So initially it was combustion noise to intermittence to thermoacoustic instability, and with synchronization theory, we have defined it as a transition from desynchronized chaos to intermittent phase synchronization to phase synchronization to generalized synchronization. So I'm not going into detail of the meaning of these synchronization states, but essentially the routes as the route to thermoacoustic instability has been redefined. And so up to this, we have looked at in the temporal domain. So transition to thermoacoustic instability or spatiotemporal transition to thermoacoustic instability has been also analyzed under the purview of synchronization theory. Now, like previous, again, we are casting this as a mutual coupling between turbulent reactive flow and acoustic oscillator. But the difference is, this time, as we are going to look at the spatiotemporal transition, so instead of looking the turbulent reactive field as an oscillator, we are going to look at as an ensemble of oscillators, right? So basically, the turbulent reactive field, which is actually image, because when we do analysis, we take image of chemiluminescence data or flame image. So each and every pixel of this oscillating or this flame heat release rate field, we are considering each and every pixel as an oscillator, which are basically the local heat release rate oscillation. Now, as we have seen in the chemical reaction, that is Belousov-Jabotinsky reaction, this heat release rate field or whatever the turbulent reactive field is actually a oscillatory medium. But for the sake of analysis, we are dividing into different grids and looking at the ensemble of discrete ensemble of discrete oscillators. Right now, with this, now we have what we have now, a ensemble of heat release rate oscillators, and that is coupled with the acoustic oscillator. So we are going to find out the phase difference between them and plotting in a field. So these are the typical phasor plot at different different dynamical states again. So as we've seen that intermittency route to thermoacoustic instability. So in different dynamical states, these are the typical phase plot. So these pattern also vary with time. So these are typical phasor plot at states, different dynamical states. So as you can see, during combustion noise, that means when the system is stable, right? So there is a small amplitude spacer oscillation. You can see these phasors are completely desynchronized. They are not synchronized at all. So you can also call it a disordered state. Whereas during thermoacoustic instability, these phasors, let me tell you, these phasors are essentially the phase difference or instantaneous phase difference between the local heterogeneous state oscillator and the acoustic oscillator. So these phasors are aligned. That means, it is not, they are, even though they are not globally aligned, at least locally they are aligned. So they show some kind of synchrony in the field. And the interesting feature that is observed during intermittency, that some of synchronized oscillators which is coexisting with a group of desynchronized oscillators. Now this kind of pattern is first observed in 2002 in an array of Stewart-Landau oscillator, where you can see these are the desynchronous phase and these are the synchronous phase at the end. And this is named in 2004 with the so after the name of a Greek mythological creature, chimera state or chimera state. So basically the spatiotemporal transition to thermoacoustic instability again redefined as a desynchrony to synchrony through a chimera-like state. Right. So far we have looked at the system, the thermoacoustic system, and this this concept also have been applied in aeroelastic system, in especially aeroelastic flutter, that is the transition to aeroelastic flutter. And in this particular system, what we did, we considered pitch and plunge, these 2 degrees of freedom, as a 2 different oscillating processes. So pitch degrees of freedom and pitch degree of freedom and plunge degree of freedom. And we have looked at how they interact when we are changing the control parameter, let's say the incoming flow. So, and with this, we basically again, this route to aeroelastic flutter is redefined from desynchronized chaos to intermittent phase synchronization to complete synchronization. So essentially the aeroelastic flutter is a transition to synchronization between pitch and plunge motions. Okay, so let us so before going into the next example, let us look back to the theory a little bit. So let us again consider 2 mutually coupled oscillators. So a very paradigmatic oscillator, let's say Van der Pol oscillator, and they are coupled. So what will happen? So in this plot, in x-axis, there is a frequency ratio. So frequency ratio is just a different representation of what we have seen, frequency difference or frequency detuning, right? So this is the same thing in different representation. So in x-axis frequency ratio, and in y-axis the coupling strength between these 2 oscillators. Now this V-shaped zone, that is essentially indicate the locking zone or synchronization zone. So when your frequency ratio and coupling strength inside this zone, the 2 oscillators will synchronize, right? And there are 2 different mechanism that is indicated by capital A and capital B. So I'm not going into detail. There are 2 standard or classical mechanism to have mutual synchronization. Now, what I want you to focus here is the green zone. So there is something interesting happened in these green zones. So when your frequency ratio and coupling strength is such that you are in the green zone, the oscillations in the 2 oscillator will completely die down, will vanish actually. And this phenomena is known as amplitude death. Now, the concept of amplitude death can be applied to stop oscillation, wherever it is unwanted. So for example, thermoacoustic instability and then aeroelastic flutter. So this amplitude death can be applied. There is a possibility to suppress those oscillations. So now the first question comes that, okay, to apply amplitude depth, you need to have two oscillators, right? So for thermoacoustic instability, there are situations when you have multiple combustor. For example, can combustor or can annular combustor, there are actually multiple combustor. And let's say all of them are exhibiting thermoacoustic instability. So all of them behaving like a different oscillators. Now can we couple them? So if so, this kind of system can be a potential application of the concept amplitude depth. So for this we have actually tried with a very prototypical thermoacoustic system, which is known as Riquet tube. So again, there is a combustion chamber, or there is a duct, that is the acoustic chamber, and inside that, instead of flame, there is actually the electrically heated wire gauge. So basically phenomena is exactly same. So if you correctly place the electrically heated wire gauge and with proper heat power, etc., you can generate sound. So you can actually generate thermoacoustic instability in the Riquet tube. So this is a very prototypical, and for a long time people are working on that. So what we have done, we have taken two Riquet tube, that is two thermoacoustic oscillator, and couple them with a very simple, through a coupling tube. So we just couple them with a coupling tube, right? Now, here you can see there is an extension duct. So that is because we need to change the length of the tube so that the fundamental frequency gets changed. And then what is actually known as detuning, that can be varied, right? So I'm going to give you an example of what we found when we change that detuning or the frequency mismatch between these two Riquet tube oscillator, right? So so the first time series, that overlap time series, shows that 0 hertz, that is the detuning is 0 hertz, when there is no frequency mismatch between the Riquet tube oscillators and there is no suppression at all. So essentially both Riquet tubes are oscillating, both Riquet tubes are exhibiting thermoacoustic instability and with the same frequency, that is they are synchronized essentially. Now if we deploy this 4 hertz detuning, there is a partial suppression. So you can see this, the amplitude of oscillation gets suppressed. So there is a partial suppression. When there is a 7 hertz detuning, you can see there is no oscillation at all. So completely vanished. So this is the application of amplitude depth. So amplitude depth occurs, and as you can see from the zoomed window, there is no oscillation at all. Whatever signal is there, it is, just the electrical noise. So there is no oscillation in the thermoacoustic system. So you can completely suppress if you properly choose your coupling parameter or detuning, etc. Now what I am not discussing, that is this pipe, the parameter of this pipe. So you can vary pipe, and that is a different kind of coupling you can introduce. So I'm not going into detail. That this is just to give you a feel that this amplitude depth concept can be applied to an application or the real system to stop oscillation. But there is one more example of which is known as partial amplitude depth. This is a 15 hertz detuning, and you can see that one of the Riquet tubes is still, it is not sounding, but the other one is the oscillation in the other one gains back, right? So in one oscillator there is a sound, in other oscillator there is no sound, so which is known as partial amplitude depth, and that can also occur if you tune your parameter like detuning or other coupling parameter, right? So yeah, as Chandan asked that there is, what is the example of force synchronization? So up to this, whatever we discussed, that is basically example of mutual synchronization, right? So there are two oscillators, etc. It can be thermoacoustic, it can be aeroelastic oscillator. So now we are going to look at example of force synchronization. Now, what will happen if we force something? So again, the forcing system will have its own frequency and amplitude, and the forced system will have its own frequency and amplitude, right? Now, what is the objective that we are going to force some any oscillator? So for thermoacoustic oscillation, as I said, the oscillation itself is unwanted. So we are targeting to suppress the oscillation, right? So for that, what we did, again, in Riquet tube, we have basically incorporated 4 acoustic driver or a speaker in the duct. So through this, basically we can send sinusoidal signal or acoustic signal to the system, right? So this behave like a forcing. This has been also implemented into a different kinds of thermoacoustic system, which is known as laminar burner. So here basically flame is there inside a duct, and here again in the upstick section in the below, you can see that there is acoustic driver or speakers are attached, and through this we are going to send the sinusoidal signal. So basically the thermoacoustic system is forced, right? And forcing signal is always a sinusoidal signal that we have taken. And what we have found that is very interesting, so even if you don't have two thermoacoustic system or two combustor, if you have only one combustor, the forcing can be a control measure. Through forcing you can actually suppress oscillation. Let us look at that. So so this is the result from this Riquet system, where the natural frequency is about 168.8 hertz, right? So this is the natural frequency, and now we are varying basically the forcing frequency. So I have shown here the 3 different forcing frequency. This is 90 hertz, 120 hertz, and 155 hertz. So basically we are going towards the natural frequency, right? Now here, when your forcing frequency is far away from the natural frequency, that is 90 hertz, the maximum suppression is observed here. So you can see that this is the uncoupled or unforced amplitude of Riquet oscillation, and here where basically the forcing started, and then after transient this will be the forced oscillation or the amplitude of the force dynamics. And you can see there is a substantial amount of suppression or amplitude suppression when you are forcing much away or from the natural frequency. Now when you are forcing with the frequency of 120 hertz, still there is a partial suppression, right? But when you are close to natural frequency, I mean there is no suppression, but there is amplification. But actually what happens, there is still suppression in the natural dynamics. So if you think about the dynamics of your Riquet or whatever oscillating processes, that is forced system, it definitely gets suppressed even when you are forcing with a frequency close to natural frequency. But at the same time, your forcing signal gets amplified. That is, we know that is known as resonant amplification. Because of resonance, that gets amplified. So eventually the coupled system behaves like the overall dynamics has amplified. So again, the forcing can be used as a control measure to suppress oscillation, but you need to choose the forcing parameter cleverly, so that the suppression happens finally and not the amplification. So in both of these studies, what we have found that, basically both of these systems, what we have found that the maximum suppression happens when your system is forced with a frequency which is close to the subharmonic. So as you can see, this is 168 hertz. So subharmonics is around 84 hertz. When it is not exactly at subharmonics, but close to subharmonics, the maximum suppression is observed, right? Now, yeah, so up to this, whatever the accomplished work I have discussed, and there are some ongoing work and also for different systems that I am going to show. So the first example is what is called natural circulation loop. So it's essentially natural convection, and because it's a passive system, because you don't need to apply any compressor or any other power source. So it's very popular in many thermal engineering application, including nuclear reactor, right? So when this natural circulation loop is designed, it is designed for a stable flow or stable flow, basically stable flow of fluid, let's say water. Now, depending upon the heater power or whatever the heat source, the temperature of the heat source, so it is essentially used to transfer heat from a heat source to heat sink, right? So depending upon the heater power or heat, the energy that is extracted from the heat source, the dynamics can change. Now, what we found from the numerical simulation, that for a 60 watt of 600 watt of heater power, there is a stable oscillation. There is no there is a stable flow, so there is no oscillation as such. Now, when the heater power is 700 watt, it shows a periodic oscillation, and when this heater power becomes 800 watt, it shows actually chaotic oscillation or the flow reversal. So we can understand that depending upon the power, this system can behave like an oscillator, whether it is a periodic oscillator or chaotic oscillator. Right. So in this system, what we are trying to investigate, again, this system, I mean, the heat transfer efficiency will be reduced if you have any kind of oscillation. And I mean, it will be, I mean, much reduced if you have a chaotic oscillation. So suppressing the oscillation or stopping the oscillation will be the objective. Now in this system also, we are trying to investigate what will happen if we have external forcing. So the physical implication can be different. So even in power source or whatever the source of heater power, there can be some fluctuation. So for make things simple, we have started with a very I mean very simple sinusoidal perturbation, and check whether how that will influence the inherent dynamics of natural circulation loop, or whether we can have some kind of suppression of amplitude. So this thing is going on. Then, as I said, that amplitude depth has been applied in thermoacoustic system. So recently we have also applied in aeroelastic system, where basically two airfoils we have coupled through a linear torsional spring, and we are trying to look at. So basically we are taking two airfoils which are basically exhibiting aeroelastic flutter, and then if we couple them through a linear torsional spring, what will happen? I mean, will there be eddy amplitude depth? So we are basically investigating the possibility of cessation of oscillatory instability in aeroelastic system using the concept of eddy. So let us show you the glimpse of whatever results we already achieved. So in x-axis, basically we varied the coupling strength, right? And in y-axis, the amplitude, the RMS amplitude of pitch and plunge, both are plotted here. So as you can see, as we increase this coupling strength, the amplitude of oscillation first starts reducing and then becomes zero. So this zone is essentially the eddy zone, where we can stop the aeroelastic oscillation. So as you can see from this time series, that this is before coupling, this is after coupling. So it actually leads to amplitude death in aeroelastic system. But the point is, if you continue to increase the coupling strength, it will then emerge into a region where there is a very large amplitude oscillation in both pitch and plunge motion, very large amplitude oscillation, which is again unexpected. So even though amplitude depth is a possibility for aeroelastic system, aeroelastic flutter, you need to choose the parameter very carefully so that it doesn't go into the this large amplitude oscillation regime. Okay. And then last but not the least, this is a very interesting system, which is candle flame oscillator. So candle flames generally doesn't oscillate. I mean, you cannot say the self-sustained oscillation for a single candle. Now, there is a reason that if you put three or more candles together or candle flames together, the flames will merge, and there is some competition between the supply of oxygen and supply of fuel, that is wax, molten wax, and because of that there is some kind of instability happens, and a self-sustained flame oscillation can be generated, right? It is called a candle flame oscillator. Now there are a lot of studies on synchronization with this very simple system. I mean, even at home you can do experiment. So with this oscillation, different kinds of dynamics, synchronization states, people have already published, and some ongoing work is also there. So basically here also we are going to look at, I mean, few new things. So just to give you a feel, what are the phenomena that occurs when you keep two candle flame oscillators side by side. So you can see this. So these are the videos. So in the top videos, you can see both the flames are oscillating very synchronously, or we can say in phase synchronization. here you can see that the oscillations are, I mean, you can roughly say that 180-degree phase difference, that is anti-phase synchronization. And this is not a image, this is also a video where you can see the images, the flames are not at all oscillating. So we have achieved amplitude depth, right? So with this, let me conclude. So yeah, so in nature synchronization is observed in the form of collective behavior. It's not only in the engineering systems, and that lead to basically the global order in the group. I mean, there are many examples in nature. The For example, the school of fish, and then uh, the massive flocking of birds. So these are the example when where basically the global order is attained. Thank you.
Thank you, Sishandu. It was really a very interesting talk. So now we are open for question. We have got already one question
Yeah.
from Dhruva Jyoti. That is like he wants to ask you what is meant by the generalized synchronization. And I will actually add to the question, how is it different from the in-phase synchronization? Yeah.
Okay. So in phase synchronization we have defined as it's just the relation between phases, right? So when we differentiate in phase and anti phase, so it's basically when phase relation is, or the phase difference is 0 degree or close to 0 degree, it's in phase. It's when it is close to pi or 180 degree, it is anti phase. Now this is for periodic oscillator. So many things that we have not talked about, that we have differentiated the synchronization phenomena as which also depends on the nature of the dynamics, like whether it is periodic or chaotic. Now if you deal with a chaotic oscillation or a oscillation where the amplitude is varying, right, then there can be different kinds of synchronization situation. And one of such situation is generalized synchronization. So in chaotic oscillation, uh, with phase, you also focus on the amplitude, what is happening to the amplitude, right? So suppose you have two chaotic oscillator which are coupled, and then you are looking at what is going on in the phase, and you find out, okay, the phase difference is 0, you can call it in phase synchronization. Then what is happening to the amplitude? Now if their amplitude is still uncorrelated, then it is called phase synchronization, just simply phase synchronization. So phases are locked, but the amplitudes are uncorrelated. Now there is another phenomena where the phases are locked, so they are phase synchronized. On top of that, the amplitudes are correlated. Then it is called generalized synchronization. And if you further increase the coupling strength, then phases will be locked and the amplitudes will be exactly same, not correlated, but exactly same. So then it is called complete synchronization. So I mean, there are different kinds of synchronization with chaotic oscillator. So general synchronization is one of them, where phases are locked and amplitudes are correlated.
Okay, so do you have any quantitative measure to differentiate when an system is generalized, synchronized, I mean, synchronized in general sense, or it is only in phase synchronized?
Yeah, I mean, phase synchronization or phase, basically the phase relation can be quantified with phase locking value. I mean, this is a very nice tool, but provided you have a oscillation where the phase calculation, that is through Hilbert transform or Hilbert transform, is valid, through which you are basically calculating phase. If that is not valid, then you can go through some recurrence measure, through recurrence, some recurrence plot also you can find out whether two oscillators are synchronized or not. And there basically the probability of recurrence is checked for two different oscillators, and it is checked basically whether the time or the amplitude of this probability of recurrence, whether they are matching or not, right? So for different situation, let's say phase synchronization, generalist synchronization, and complete synchronization, this recurrence plot, I mean, qualitatively they can give you, I mean, they can help you to distinguish these different phenomena.
Okay, fine. Yeah, I think Venkat has some question. Please switch on your camera if you feel free and then ask the question. Yeah, please.
You are not audible, Venkat.
Are you muted? No, you are not muted. Okay, he's typing the question. Okay, so we'll take that question. So I had
Yeah.
another question in that sense. Yeah, please.
Sorry, yeah, sorry.
Yes,
I
please
have
go
a
ahead, Aswati.
yeah, yeah, yeah. So, thank you. It was a very nice talk. So my question is, okay, for regarding your first slides, for the system to for the concept of synchronization to be valid, you said the oscillators have to be self-sustained, right? So
Yes.
is it like the coupled system has to be self-sustained, or individually each of the oscillators have to be self-sustained?
Each of the oscillator, whatever oscillator you are taking, those oscillators should be self-sustained.
Yeah,
They
okay.
should
In that
not
case,
maintain oscillation I mean, by kicking or by kicked by the external source, etc. So they should have self-sustained oscillation.
okay. Yeah. So then, in the thermoacoustic system, are the acoustic oscillator, if you decouple it from the flow, or the flow oscillator, if you decouple it from the acoustic signal, are they individually self-sustained? Because they will damp out, right? At least one of them.
Yeah, right. It's a good question. So when we say that self-sustained oscillation, I mean, definitely, I mean, in thermoacoustic system, when we think about acoustics and turbulent reactive flow field, we need to prove that they are self-sustained. And now think about a situation that you have a flame that is a turbulent flame, but it is not confined, right? So if it is not confined, I mean, there is no interaction with the acoustics, although there is a pressure variation, but it is no interaction with the acoustic as such. So now if you think about the heat release rate oscillation, there will be heat release rate oscillation because of the turbulent flow field, unsteady flame dynamics, etc. So it will be chaotic because of the underlying chaotic nature of turbulent flow field. And then, I mean, that way you can say that your heat release rate oscillation, that is there even though there is no confinement. So that is one situation. In another situation, if you can think about, there is only a duct, nothing else, right? Only a duct is there, and there is no flame. So even then, inside a duct, there will be the fundamental frequencies which will not be triggered because you are not giving energies, but those frequencies will be there. So if you just uh, measure the pressure inside a duct, or only flow is there inside a duct, so you will have a very aperiodic signal, aperiodic pressure signal, which actually reflect all the modes of your all the modes of the, so fundamentals and the harmonics of whatever the duct possess. So in that way, I mean, they are self-sustained, but it is sometimes not visible or audible depending upon how much energy is there. So initially, if you think about the thermoacoustic system itself, right? So that means at the stable combustion. So if you look at the heat release rate oscillation, it shows aperiodic oscillation. If you look at the acoustic oscillation, it also shows acoustic oscillation or aperiodic oscillation. But sometimes we find that there is a little higher peak in the fundamental mode of the combustion chamber. But as we increase this coupling parameter, that means as we increase the coupling between these two oscillators or oscillating processes, they basically gets energy to each other, and then the amplitude of oscillation grows. So with this, let me also uh, uh, I think that will be the follow-up question. Then what will happen in the pitch and plunge in aeroelastic flutter?
Yes,
So
exactly.
even, yeah, right. I can Yeah. So basically, even in aeroelastic system, uh, let's say I mean, that is a very simplified form of airfoil that we are considering 2 degrees of freedom. Now, if we simplify more, we can have a single degree of freedom. So suppose a airfoil is oscillating with only pitch or only plunge. So that will not be flutter. So for flutter, definitely you need to have 2 degrees of freedom and interaction between them. But you can have a pitch motion or plunge motion separately. So essentially that means, so for having pitch motion or pitch degree of freedom, you don't need plunge degree of freedom, right? So they can be separated. I mean, it cannot be, I mean, it's how you perceive that oscillation, that's a different thing. But the 1 degree of freedom airfoil, I mean, can be made, and that is, there is a possibility. So, but when you are considering 2 degrees of freedom together, and there is a possibility of flutter, and that transition is described as a synchronization.
Okay, so the pitch oscillation, if you consider it individually, say only the pitch oscillation is there, it is described by a damped differential equation, right? So depending on the parameters of your system, it can have a damped oscillation, no? If there is no forcing, because there is no coupling.
Yeah, it will be damped oscillation. But the damped oscillation, when you are basically considering the uniform flow, or it's a, I mean, there is no noise or there is no turbulence in flow, etc. Right? But there can be, I mean, small amplitude oscillation or vibration.
You're saying there is a flow coming. So I'm saying without the flow, it's then only we can call it uncoupled, right? There is no forcing term.
No, I'm not talking about the coupling between flow, the structure and the flow. That will always be there. That coupling is always there. When I casting the system as pitch and plunge, I am just separating the pitch motion and plunge motion separately. But still, there is a fluid structure interaction is there.
Oh, okay.
If that is okay. And
yeah.
if there is no non-uniform flow or some turbulence fluctuation is present, then your the pitch motion or whatever oscillation can be there with some aperiodic oscillation.
Yeah.
Yeah, please. Absolutely.
One more last question, sorry. So you said we can't put in the concept of sync when there are two variables which are connected, right? Like displacement velocity. So aren't pitch and plunge like that? Because one varies, the other also varies. Or can they be differentiated? I'm not very sure of this.
Yeah, that is the, I mean, same answer. I mean, whether we can separate these two oscillators or two oscillating processor or not. I mean, if they can be separated and still exist, I mean, these oscillations, then we can call them as self-sustained oscillation. If we cannot, then there will be, again, I mean, that is true for thermoacoustic systems also. I mean, if you think about flutter or thermoacoustic instability, they cannot be separated. But if you just separate, I mean, there will not be flutter, there will not be thermoacoustic instability. There can be separately heat reduced jet oscillation or acoustic oscillation. And here also, I think pitch oscillation and plunge oscillation can be there separately. If we just think about 1 degrees of freedom airfoil.
Okay, thank you very much. Thank you. It was a very nice talk.
Okay, so before going to Venkat's question, just to add with Aswati's question, I have another follow-up question. Like, so don't you think that the concept of force synchronization defies this definition that we need two self-excited oscillators? Like, because that is happening through a forcing. So where does the definition of synchronization come?
Yeah, even in forcing, we need to have two self-sustained oscillators. When you think about,
so you are basically superimposing a force over a synchronized system.
Not over a synchronized, over a self-sustained oscillator. So when you think about a situation of force synchronization, it's not that like a magnetic pendulum. So without the magnetic force, the pendulum will not oscillate. Right? So only by magnetic forcing, this is oscillating. So this is complete resonance, or I mean, so this is not a force synchronization. This can be a forced oscillator. Together you can call it a kicked oscillator or forced oscillator. So a pendulum and a periodic magnetic field. But force synchronization is, even if there is no forcing, there will be a self-sustained oscillation. And the forcing system is also a self-sustained oscillation. And then it is the forcing system is influencing the force system. But both are again self-sustained oscillation.
Okay, but only thing that there is no feedback synchronizing force from the second oscillator.
Yeah, no, it's unidirectional. So there will not be mutual interaction.
Okay, so let's go to Venkat's question. So the first question he has is, what exactly does nonlinearity do to facilitate sync?
Okay, so basically, nonlinearity, I mean, to have the self-sustained oscillation, you need to have nonlinearity. And then whether that will be sync or not, that depends upon the coupling parameter or detuning, etc. Right? So, I think you are talking about the nonlinearity in the system, that is in the oscillator. So that is, in the first place, you need to have nonlinearity to have a self-sustained system. Right. So if you think about linear oscillator, that need to be forced, and then again we cannot call it a self-sustained oscillator. And if you think about the nonlinearity in the coupling term, there are possibility for both. Like if you take the linear coupling or nonlinear coupling, in both the cases there will be synchronization, amplitude, depth, etc. So a lot of possibilities are there. I mean, depending upon the situation or uh, the phenomena you are modeling, you have to incorporate nonlinearity, linearity, nonlinearity, etc. But the nonlinearity in the system is evident to have the self-sustained oscillation.
Okay.
Given that synchronization is found in nonlinear system, and nonlinearity is largely used to define system which define superposition principle, what exactly does nonlinearity do to produce needed sync?
I think it's almost the same thing what you
Yeah,
answered.
yeah.
The second point what he has, that the type of nonlinearity, can it change the synchronization route? I mean, we have seen it can change, but what is the underlying physics probably? Like why it changes?
I mean, again, I mean, nonlinearity in the system you are talking about, the self
Yes.
oscillation system.
Yeah, let's say we have self-excited system with two different kind of nonlinearities, right? So
Nonlinearity.
how
Right.
will it affect the synchronization scenario?
Yeah, so honestly speaking, I am not in a position to answer this question. Yeah,
Yeah,
that
yeah,
needs to be
it's
checked,
we
but
we are
there are
still
different
working
kinds
on
of,
that. Yeah, I mean,
right, yeah.
yeah, so the other question that I had adding to Aswath is that, like, when you are actually let's say you talked about a single degree of freedom system, right? So even flutter can happen there if it is considered to be a stall flutter, let's say, due to the flow. So in
Okay.
those cases, should we not consider the flow as the oscillator first and then structure as an oscillator, because the synchronization is happening between the flow and the structure, right? So obviously there is a existing oscillator kind of system which is coming to the nonlinear flow or whatever flow model. So
Right.
like that there is a confusion. So basically we are not considering that. So basically we are not checking the phase synchronization between the flow velocity and the plunge or pitch, but we are just
Right.
checking between plunge and pitch. So as if there is two oscillator in the flow.
Mhm.
So I understand your point that we are checking the synchronization between those two, but should we not
Right.
check the synchronization between the flow properties and the oscillator?
Yes, sure. I mean that is the basic feedback or positive feedback to have flutter. So when you define flutter, that is basically a feedback between fluid and structure. So definitely they are interacting and mutually interacting. So it is a good idea to check that how they are interacting, what is the synchronization phenomena. Now again, uh, so if you just separate flow and the structure, and then you have to again prove that so flow, it is easy to prove that flow, if it is a turbulent or something, that flow there is a oscillation, but for structure you need to prove that is a self-sustained oscillation. So once you can prove that structure itself is a self-sustained oscillator, flow separately a self-sustained oscillator, it can be checked.
Okay. Yeah, so Venkat has added another question. Can you just see that?
Yes. Is the nonlinearity needed only for the self-sustained oscillation? To my understanding, nonlinearity does not guarantee self-sustained oscillation. Yeah, it does not guarantee self-sustained oscillation, but if you don't have nonlinearity in the system, then I mean, even if you have nonlinearity, it can damp out. But if you have a linear system, linear oscillator, that needs to be clipped. So for that, self-sustained oscillation is difficult.
Okay.
So even though it is not, I mean, the nonlinearity guarantees the self-sustained oscillation, but it is needed to. I mean, for a self-sustained oscillation, the nonlinearity must be there. Can we consider this mx double dot plus kx is equal to 0 capable of giving rise to sustained oscillation?
No, it's linear, right?
Sustained oscillation for a given initial value, then to feed the need for sustained oscillation. Nevertheless, okay. So, I mean, here basically you are not considering the damping term. So that means it's basically a conservative system. So that is again, I mean, if you something can be modeled like this, there is no dissipative term. That means completely conservative system like electron is moving. Then it can be considered as self-sustained oscillation. But most of the dissipative system, which are non-conservative system, you have to have damping, and then it will die down until or unless you have some forcing term or non-linearity.
Okay. So by self-sustained, are you implying referring to limit cycle oscillations? Yeah, mostly. I think so.
Yeah,
Do you want?
self-sustained. I mean, no. I mean, okay. So it has nothing to do with limit cycle oscillation. I mean, self-sustained oscillation can be chaotic oscillation. So
Yeah, true.
self-sustained mean, I mean, the energy source is there inside, or there is a continuous supply of energy. So it should not be damped out. So there are three properties we have discussed. So those are the basically properties of self-sustained oscillation. I mean, whether it will be periodic oscillation, that means limit cycle oscillation, or chaotic oscillation, that depends upon many parameters. Right?
Okay. So do we have any other question from the audience? Please keep posting. By the meantime, yeah, I have a question. Like, can you give any physical example in nature, maybe, where we see chimera structures? Like the interplay between asynchrony and synchrony in the spatio-temporal domain, as you said. So, like, do you have something in mind, like just out of curiosity?
In nature, I mean, there are other systems where chimeric transition have found, but not that is spontaneously. I mean, people have first tested in the theoretical model, that is Landau oscillators, and then the first example that came up, that is again the mechanical oscillator. Uh,
Yeah,
that is
but
with
I mean,
metronome. So
what is
people have.
the underlying motivation? Like, I mean, does it trigger to any natural phenomena or something? That's just
Mm, Okay, so I can only comment on what we have, how we look at the thermoacoustic system. So during intermittency, when we have chimeric state or a location where the group of oscillators exist and a different location group of desynchronized oscillators also exist, so that essentially corresponds to a coherent vortices. So basically, whenever there is a group of oscillators that are those are in sync, so we found that is the location when a coherent vortex is generated or formed, and that is traveling towards the black body or whatever in the flow field. And if that is not there, then again the heat release oscillations are in, I mean, they are not in sync. So that is the relation we found, that whenever there is a coherent vortex, so that corresponds to a group of synchronized oscillators. and and that is one way we can think of that. When we have the whole field synchrony, I mean the synchrony in the total reactive field, and that gives rise to thermoacoustic instability. So essentially we have to disrupt the location where the coherent vortex is generated, because that is the, I mean, in the later studies, it is also shown that this location where a group of synchronized heat release oscillators are there, those are the source of energy. I mean, those are the location where the energy is transferred from combustion to acoustic field, right? So when we target some say pinning control or to stop the oscillation in thermoacoustic in a thermoacoustic system, so we need to look at those locations where the coherent vortexes or vortices are there. So people have also tried with pilot air jet or fuel jet, so that they can disrupt the formation of coherent vortex, and then disrupt this synchronous or the formation of this synchronized group of oscillators or synchronized group of heat release oscillation, so that eventually it cannot lead to the global synchrony and thermoacoustic instability. So that is one example that, I mean, that we can think about from this chimeric structure, and some follow-up studies also have been made and published that what is happening when there is a synchronized oscillator. Uh,
Yeah,
yeah,
I
so
mean,
this much I can
yeah,
say.
in
And
terms of the fluid mechanics and theory of turbulence, the exact same definition comes for intermittency in spatiotemporal domain, like where a large coherent structures breaks down to small eddies through the Richardson cascade, and it happens in different patches, and which is with nothing but chimera structure as per your definition. And it's
exactly.
actually for long time it is known that those are the regions of intermittency which through the chaotic route transition to a complete turbulence. So yeah, I was just curious if this is similar. So we can call them also the chimera structure, right?
Yeah. I mean, we can probably, but here the basic difference is when we think about thermoacoustic system. I mean, the whole parametric regime that we are dealing with, stable combustion to unstable combustion, we actually deal with a very high Reynolds number, that is a turbulent flow. So even we have a very high Reynolds number, the system is actually moving from disorder to order. So that is what is very interesting here. So even though we're starting from a turbulence and the disorder, then with this coupling between pressure and heat release rate, it is actually moving towards an order and through chimera state.
Okay. Okay, so I don't think any other question is coming from the audience. So I will end with the last question. So as you have given already an example of fish schooling, so currently we are doing a very exciting study with fish swimming in pairs or groups from the experimental data where the fishes are swimming against the flow. So it is very nicely the same synchronization route is observed. But my question is there, I mean, there is a query that when two fishes started swimming against the flow, right? So they comes in synchronization, either in phase or out of phase or intermittently. But the thing is, they are controlling their motion through a signal from their brain, right?
Right.
So do you consider it to be but they are interacting mutually, making a constant
Exactly.
position. So is it a forced
Exactly.
synchronization or a mutual synchronization?
No, when, I mean, as two pieces are, I mean, they are affecting each other, it's again a mutual synchronization.
But there is a forcing signal from their brain. So, I mean, without which it would not have happened because they are controlling their motion, right?
Yeah, right. I mean, the fish with its brain, it can be considered as a self-sustained oscillation, because even if you allow a single fish into the flow, it will oscillate and it will go. I mean, it will move in oscillation, right? So let us consider a fish itself is a self-sustained oscillation where the brain basically acts as a kind of what we can say code or decode the whatever signal that is coming, and then sending the signal to the actuation system of the fish, etc. Right. So fish, I mean, the brain is not leading the motion, or you can think of, yeah, it's leading the motion of a fish, but whatever it is deciding on based on the other fish. So it is basically getting signal from the other fish, and then
Yes, I would
process
not
that
say
signal,
that
and then
signal. I would say that it is getting the fluctuations from the flow, because again here flow is the medium. So it is whether it is getting benefited in terms of energy or swimming.
Okay.
Based on that, it is deciding. Yeah. So yeah, I understand. So we can call it mutual synchronization.
Right. Right.
Right.
Yeah, just one, I mean, one statement to add. So if you just think about the fish and its brain to different system, then this, whether forced by brain or forcing by brain, I mean, the fish oscillation is forced by brain signal, those things will come into the picture. But when you think about the fish with its brain, a single oscillating process, and the other fish with their, I mean, its brain is another oscillating process, then whatever transformation is happening, that is completely mutual. I mean, it may be through flow, it's completely mutual, and so we can call this as a mutual coupling or mutual synchronization.
Understood. Yeah, very interesting talk indeed. And I think there are no questions from the audience also. So uh, on behalf of the audience and the team, let me thank you again for giving this beautiful talk. It's very interesting. And let us call it a day. But before that, I just want to announce that the next talk from this initiative is on 10th October, where an engineer from Airbus will talk about industrial application, and it will be very interesting. So please try to attend and keep a track on the website, themechanicsdiscussion.com. Thank you, everyone. Okay, so we are ending the meeting here. Thank you. Have a good day.
Thanks.